All right, everybody, welcome to Math with Grace. Today we're going to be going through Algebra 2, Book 4, Lessons 1 through 5. Lesson 1 begins on page 2, and it's titled Factoring Completely. We've talked about factoring, factor, how important it is to make sure you're factoring everything you can. And so the topic that they want to cover today is when every term in a polynomial has a common factor, to factor it out first and then factor in other ways. And so, for example 1, we have 12x squared y plus 8x squared minus 60xy minus 40x. All of these have the factor 4x in common. And so we can factor that out of each term. And then we can look into factoring this more completely, and they factored by grouping, okay? For this example 2, 18x to the third power plus 60x squared plus 50x, they all had a 2x in common. They factored that out. This is what was remaining, and then they were able to see that this was a perfect square here and a perfect square here. Therefore, it was a perfect square binomial, okay? So, as always, factor. It's the most important thing that we need to do, because we have to factor before we can cancel and all these other things. So this is just another set of practice problems for factoring. So let's take a look at these problems together. All right, we are in Algebra 2, Book 4, Lesson 1, page 2. Problem number 1 is 6x squared y plus 4x squared minus 36xy minus 24x. All right. Looking at this, 4 is my smallest coefficient, so that is what I need to look at to figure out what can I take out. Well, 4 doesn't go into 6 evenly. It does go into the other two, but that doesn't matter because it doesn't go into 6 evenly. So that tells me my factors of 4, which are 2, goes in, right? They're all even. So 2 is the coefficient that I'm going to be able to pull out numerically. Now let's look at the variables. Over here, these two terms both have a single x. The other ones both have an x squared, so I know an x can be pulled out. Here we have a y, but a couple of terms don't have y's, so it's just going to be the 2x that gets pulled out. So now we need to basically divide each term by that 2x and see what's left behind. So 2 goes into 6 3 times. X is an x squared, so there's going to be one extra x, and then the y is not bothered, so that's there. 2 goes into 4 2 times, and I can take 1x away, and there's 1 left. 2 goes into 36 18 times. I'm taking the 1x away, but there's a y left. And 2 goes into 24 12 times, and then we took that x away. All right, so here is what we're left with. Now we kind of need to group it together so that we can factor out some more. So I'm going to rearrange these a little bit. So I have 2x times the quantity, 3xy minus 18y, okay, plus 2x minus 12. Now within here, I'm going to factor by grouping with these two groups. So I have 2x times the quantity, right? What am I pulling out of here? Well, they have a 3 and a y in common. So it's going to be 3y times, this is leaving an x behind, and here is going to be a negative 6, okay? And then over here, these two terms have a 2 in common. So I'm going to pull the 2 out, and that leaves an x minus 6. All right? So now I need to finish this factor by grouping. So I have 2x times 3y plus 2 times x minus 6. And I have factored completely. Okay? Now, the instructions don't want us to solve for anything. So, factoring completely, and we have completed it. Okay? Number 2, 5x squared plus 10x plus 5. All right, well, they all have a 5 in common. So let's take out a 5, and that leaves x squared plus 2x plus 1. So now, what factors of 1 add together to give me 2, right? That's what we need to be thinking about here. Well, 1 times 1 is 1, and 1 plus 1 is 2. So I have x plus 1 times x plus 1, or basically x plus 1 squared. X squared is a perfect square. 1 is a perfect square. So this becomes a perfect square binomial. All right, let's take a look at the next two. For number 3, we have 2x squared y minus 72y. And definitely a 2 is coming out because they are both even numbers, right? And they each have one y, so we can pull out a y. That leaves behind here an x squared, and a minus 2 goes into 7 3 times, you carry the 1, 36, okay? 2 goes into 12 6 times, and I can take the y away, so that's that. Now, you might be like, okay, I'm done, but let's look more closely, because this is a perfect square and this is a perfect square. This has a negative sign in between, and therefore we know we can factor it more. Okay, so we have 2y times 2 sets of parentheses, right? My x's break apart. My 36 becomes a 6 and a 6. And because this is negative, I have one positive and one negative, right? This is the result of a perfect square, or sorry, sum and difference binomial. This is the product of a sum and difference binomial. And so we need to be able to recognize those things. When we have two perfect squares, if this was a plus, then it doesn't work, right? There, we can't factor that any farther. But when it's a negative sign, we can factor it to that sum and difference binomial. Okay, so that's what we're talking about when we're saying factor completely. We got to look. But don't just, if this was a plus sign, don't just factor it because you think it's right, because that doesn't work out the same. Okay, number 4, 9x squared minus 6x minus 3. Well, all these things have a 3 in common. This does not have any variables, so I can't pull any of those out. 3 goes into 9 3 times, but I still have that x squared. 3 goes into 6 2 times, and I still have that x. 3 goes into 3 1 time. Okay, so now is 3x squared minus 2x minus 1 factorable? And this is factorable. If we took 3 times a negative 1, right, this coefficient times this constant, we would get a negative 3. The factors of negative 3 are 3 and 1. Well, one of them has to be negative, and it would be this negative 3, okay, would give me a negative 2, and I added these back together. So 3 times 3x squared minus 3x plus x minus 1, okay? Now we've split our factors apart. We've split this negative 2x apart to a negative 3x plus 1x. Same, if we combine them back together, we'd be right back where we started, right? We're splitting our factors out, and now we can factor by grouping. And it's going to look like that. So 3 times the quantity. Here we have a 3 and an x in common, and we leave behind an x minus 1. And then this is already an x minus 1, okay? So now we need to complete our factoring by grouping. So 3 times x minus 1, we're factoring that out, and it leaves behind 3x plus 1. Don't forget there is a 1 right there. Okay, and now we've completed our factoring. All right, so sometimes up here, all we had to do was rearrange, or sometimes you don't even have to rearrange, but all we had to do was set up our grouping. We pulled out a single term, and then we set up our grouping, and we factored by grouping, right? Here, all we had to do was factor out a constant, and here we just factored out a term, okay? But in this case, we had a sum, the product of a sum and difference binomial, so that's where we went with that one. This one, we factored out a constant, but then we had to break apart, we had to factor our linear term, our middle term, we had to break apart those factors and then factor by grouping, okay? Each one of these is a lesson or a technique that we have learned so far. Each one of these is a different technique that we've learned so far. All of them have a little bit of the same things together, but they're all a little bit different. So we've got to remember our factoring and do our best to get each piece factor it out. If you get stuck on one, let me know, and I'm happy to help you work through that, okay? That's lesson 1. Go ahead and finish the rest of the problems, and I will meet you back here for lesson 2. Lesson 2 begins on page 5, and it's titled Factoring a Difference or Sum of Cubes. So we've done a sum and difference binomial, right? But now we're talking about a sum or a difference of cubes. And so that's what this looks like. Here is a difference of cubes. Here's a number cubed and a number cubed, right? Here is a sum of cubes. Now, each of these factors into a specific pattern. Not something I normally say memorize, but you might want to fold this page over so that you can reference these patterns. But let's go over how these patterns are made. The binomial for a difference of cubes, okay? So the binomial for a difference of cubes, this is the binomial part, is also a difference. So if this is a minus here, the binomial part is going to have a minus. The binomial factor for the sum of cubes is a sum. So if you have a sum here, then you're going to have a sum here. The first and last terms, okay, the first and last terms of the trinomial factor are always positive. So positive, positive, this term here, positive, 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 positive. I'm like, wait, we messed up. But no, the square part is always going to be positive, and this square part at the end is always going to be positive. Now the middle sign, this sign here, is basically opposite what you started with. So for a difference, it's going to be positive, and for a sum, it's going to be negative. Okay? So the binomial part matches. The other term is the opposite. The other middle term is the opposite. Okay? So let's take a look at some of these. Example 1. I'll try to leave the gray box on screen. There we go. Factor 8x to the third minus 27. Okay, so here is just a matter of recognizing that these are cubes of something, right? 8 is 2 cubed. 27 is 3 cubed. Obviously, x to the third power is x cubed. So then what I like to do, they don't really set it up too close. I mean, they kind of do it right here, but I like to identify my a and my b. So my a is going to be the cubed root of, this should be 8x to the third. But I know that the cube root of 8 is 2, and the cube root of x to the third power is just an x. So my a is 2x. My b, looking here, my b part is 3. 27 is 3 cubed. So then they set up their binomial portion, right? And remember, the binomial is going to match what we started with. And then after that, to fill in the rest, we just have to look here at this formula, okay? And the formula tells me that this part here should be a squared plus ab plus b squared. So to know what to put here, you take your a and square it. 2x, the quantity squared, is 2 squared plus x squared, or 4 squared. For this AB portion, we're just multiplying our A and our B together. So 2x times 3 is 6x. And for the B squared portion, we just square our B. And in this case, it's just 3 squared, which is 9. Okay? So I don't push memorization, but you kind of need to know. So you need to be able to reference it. I would fold this corner down or something so you can reference these formulas. Okay? So then looking at example 2. We have 64a to the 6th plus b to the 9th, okay? Well, again, we have to see 64 is 4 cubed, right? A squared, so a to the 6th power, if you take the cube, oh, it's over here, cube of a to the 6th, I'm not sure why these are so big, right? Remember when we take a root of a variable to a power, it's how many times does this index go into the number of the exponent. Well, there are 2 3s and 6, so that gives me an x squared. Okay? So my a is going to be 4, not x, well, I didn't x there, but this is 4a squared, okay, because we're dealing with a's and b's, and b to the 9th power, if we take the cubed root, how many 3's go into 9? Well, there are 3, so this is b to the 3rd power is what would come out, okay? So b to the 3rd power cubed is b to the 9th. So my b, in this case, I wish they hadn't used a and b again, but that's okay. My b is going to be b to the 3rd power. All right? So now the pluses match, right, for the binomial. And so you just put in your a and your b. For the second part, it's a squared minus ab plus b squared. Okay? So a squared, 4a squared, the quantity squared, 4 squared is 16, a squared to the second power, a squared squared, right? You multiply your exponents, so it's a to the 4th. The next one is a negative a times b, okay, so 4a squared, b to the 3rd power. And then the final term is b to the 3rd power squared. B to the 3rd power squared. And remember, when we take a power to the power, then we multiply our exponents and we get b to the 6th power. Okay? All right, let's take a look at these problems together. All right, we are in Algebra 2, Book 4, Lesson 2, page 5. I've written our difference and sum of cubes here as a reference. So problem number 1, 27m to the 3rd minus 8. Okay. We've got to recognize these, okay? My a is the cube root of 27, which is 3, and the cubed root of m to the 3rd power, which is just an m. My b, okay, in this case is 2. 2 cubed is 8. We've got to recognize these, all right? So now, how do I write this? This is a difference, right? So I'm going to write a minus b times the quantity a squared, which is 9m squared, plus ab, or 6m, plus b squared. Okay, just following this pattern right here. I know I got a little messy, but following that pattern right there. Okay, that is our factor. Look at number 2. I didn't give myself enough room to do these. Looking at number 2, I have a to the 3rd plus b to the 6th. So my a is a, right? The cubed root of a is just a. Or sorry, the cubed root of a to the 3rd power is just a. It's like canceling itself out. It's like the square root of x squared is just x, right? So what is my b then? Well, my b is the cubed root of b to the 6th power. 3 goes into 6 2 times, so it's going to be b squared. Okay? So now, writing out my factor, this is a sum, so I'm going to have a, which is a, plus b, which is in this case b squared, times the quantity a squared, minus ab, so ab squared, plus b squared. So remember, the b squared is b to the 2 times 2, or b to the 4th power. Okay? That's what that looks like. All right. Super messy, but let's look at number 3. We have 64 x to the 6th power plus y to the 3rd power. Now, the cubed root of 64 is 4. So my a is a 4. X to the 6th power, if we take the cubed root of x to the 6th power, okay, 3 goes into 6 2 times, so it's x squared. So my a is 4x squared. Now, my b is the cubed root of y to the 3rd power. The cubed root of a power of 3 is just the radicand, so it's just y. Now we can start setting up. We have a sum again, so it's the quantity a plus b times the quantity a squared. So 4x squared, the quantity squared, which is basically 4 squared, and x squared squared, okay, which is x to the 4th power, minus a times b, or 4x squared y, plus b squared, which is y squared. Okay, that's a big one. All right, let's do the next 3. All right, for number 4, I gave myself some more room this time. We have 8a to the 9th minus b to the 9th. So we need to figure out our a and our b. Well, we know that 2 cubed is 8, so we have a 2 here. The cubed root of a to the 9th, okay, 3 goes into 9 3 times, so it's a to the 3rd power. For my b is also to the 9th, so it's going to be b to the 3rd power as well. This is a difference, so I know that at first I'm going to have a minus b, that quantity times a squared, so 4a to the 6th. Remember, when we square power to the power, we multiply our exponents, so it's a to the 3 times 2, plus a times b, so 2a to the 3rd, b to the 3rd, plus b squared. So b to the 3rd power squared is b to the 3 times 2, or b to the 6th power. All right, there's a pattern, and we have to understand and learn the pattern, okay? Number 5, we have 1 minus 1/8 x to the 3rd power. This might not look it, but it is still a sum or a well, this one's a difference of cubes. So my a, this cubed root of 1 is 1. 1 times 1 times 1 is 1. For my b, this 8 is still a cube root of 2. So it's 1/2, okay? And x to the 3rd cubed, the cube root of x to the 3rd is x, right? Okay, now that we have that established, this is a difference. So I'm going to have the quantity a minus 1/2, or minus b, right? A minus b, which is 1/2 x, times the quantity a squared, still a 1, plus a times b, 1 times 1/2 x is 1/2 x, plus b squared. Okay, 1/2 x, the quantity squared, is equal to 1/2 squared times x squared. 1/2 squared is 1/2 times 1/2, or 1/4, and then we have our x squared. Okay, break these out if you need to understand what needs to happen there, okay? We've got to distribute this squaring, basically. Okay, so that's number 5. Gave us a fraction, didn't phase us at all. We had this in the bag. All right, number 6. 125 a to the 12th plus 64 b to the 9th. All right, 125, if you're not sure, is 5 cubed. So for my a, I have 5, right? And then I have the cubed root of a to the 12th power. 3 goes into 12 4 times, so this is a to the 4th. For my b, remember 64 is 4 cubed, so I have 4, and we already done these to the 9th over here, right? So we know that this is b to the 3rd power. So now we can lay out our pattern, right? This is a sum, so our first the binomial part is a sum. So we have the quantity a plus b times the quantity a squared. Okay, I'm going to break it down for you. 5a to the 4th, the quantity squared. We've got to distribute our square, so it's going to be 5 squared times a to the 4th squared. 5 squared is 25. A to the 4th squared, power to the power, is a to the 4 times 2, or a to the 8th power. Okay? Minus a times b. So 20 a to the fourth, b to the third, plus b squared. So 4b to the third squared. We're distributing the square, so that's 4 squared times b to the third power squared. 4 squared is 16. B to the third squared, power to the power, is b to the 3 times 2, or b to the 6th power. Okay? Just barely squeeze that one in. That's a chunky one, but still nothing we can't handle. Okay? This pattern is very important. If you didn't already mark your page, you might want to think about it, because the pattern is what's important here. Once we identify what our A is and what our B is, we're just simply filling that into the pattern. Okay? That's lesson 2. Go ahead and finish the rest, and I'll meet you back here for lesson 3. Lesson 3 begins on page 7, and it's titled Rationalizing Radical Denominators. It says the standard practice for simplifying radical expressions requires eliminating radicals in the denominator. You cannot have an answer that has a radical in the denominator. It is not allowed in math. So to do this, we multiply both the numerator and the denominator by a radical that will result in a perfect root in the denominator. So here are 3 examples we're going to go through. For number 1, we have the 5 over the square root of 3. Now, we cannot have a denominator with a radical in it. So we're going to multiply this fraction by a factor of 1. This is square root of 3 over the square root of 3 is 1, right? But we chose the square root of 3 over the square root of 3 because down here we have a square root of 3. And when we multiply these two things together, we go this way, right? Square root of 3 times the square root of 3 is actually a perfect root, and then we're able to get rid of the radical sign. Now, a lot of people will be like, oh, this cancels, but then you're stuck right back where you were, 5 over the square root of 3. So do not cancel in that manner, okay? Because that is not going to help you in any way. When we do these kinds of problems, we're meant to multiply straight across. So when we do, we get 5 times the square root of 3 over 3. And if we could reduce further, we would, but in this case, we cannot. All right, so looking at example 2, we have 2 over the cubed root of 5. Now, for this particular one, we don't want to multiply it by the cubed root of 5. I mean, you could, but you don't need to, because all we need under here are 2 more 5s, right? Then we would have the cubed root of 5. Sometimes it doesn't matter if you do that or not, but we want the smallest possible number, so we don't want to have to factor and factor and factor afterwards. So we're going to multiply this. We only have 1 5. We basically need 2 more 5s under there to give us 3 5s to be able to pull that 5 out, right? So we're going to multiply by a factor of 1 in the form of the cubed root of 25 over the cubed root of 25. When we multiply these together, obviously in the numerator, we'll have 2 times the cubed root of 25, but here we'll have the cubed root of 5 times 25, and of course 25 is 5 times 5. So now we have the 3 5s we need to pull that 5 out. Okay, that's what we're talking about when we want to multiply it by something to make it a perfect root. And this made it a perfect cubed root, and we were able to pull out that 5. Okay? If we had just multiplied this by the cubed root of 5, right? And if we had just multiplied it by the cubed root of 5 again, this would just be the cubed root of 25, which is not enough 5s. So in this case, we had to multiply it by 2 5s. Okay, does that make sense? 25 is 5 times 5, so it's 2 5s underneath there. Here we just had a square root, so we only needed 1 more 3 to finish it. Now for problem number 3, it's a slightly more complicated. We have 3 times the 4th root of a to the 3rd b over 2 times the 4th root of 8a squared b to the 3rd. Now, we only want the denominator, we only need the denominator to be without a radical. So that's what we want to focus on. So we need to look here in our denominator and decide what do we need to multiply this by to get these things to be perfect roots. Well, remember, 8 is 2 times 2 times 2. So we only need one more 2 to make this a perfect fourth root. And so that's what they've done. Here's a 2. Now a squared is 2a's. We only need 2 more to make it a perfect fourth. And so they have a squared. And then b to the third just needs one more b. So here, b. So that's how they decided what to multiply by. And they are doing it in the form of 1 to keep the equation the same. Remember, we don't want to change the equation. So this is in the form of 1. Okay, it just looks like that instead of a 1. But obviously this over itself is 1 that could cancel out, but we don't want to cancel, right? We want to multiply through. So when they multiplied it through, here's what they got. Here's what they had left, right? So they had 3 times the fourth root, because here's our 3, times the fourth root of 2. A, in this case, in the numerator, it's a to the third times a squared is a to the 3 plus 2, or a to the fifth. And then b times b is 8b squared. Now, this needs to be simplified, right? Because 5 is bigger than 4. So definitely can pull an a out, but we'll deal with that in a second. And then in the denominator, okay, they went ahead and multiplied it through first, which is fine. We have 2 times the fourth root of 8 times 2, which is 16. A squared times a squared, which is a to the fourth, and b to the third times b, which is b to the fourth. Now that needs to be simplified as well. In the numerator, like I said, 4 goes into 5 one time, so we could pull out 1a, but it left 1 behind there. And then in the denominator, the fourth root of 16 is 2. The fourth root of a to the fourth is a, and the fourth root of b to the fourth is b. And then we can simplify that even further here by canceling the a's from the one from the numerator and the one from the denominator. And we finally get our final answer. So from example 3, you can see this can be a somewhat steppy process, but we need to make sure we're factoring and reducing completely. We've got to reduce completely. All right, let's take a look at these problems together. All right, so we're in Algebra 2, Book 4, Lesson 3, page 7. Problem number 1 is 3 over the square root of 2. Now remember, for square roots, we only need 2 of something to be able to pull it out. So we're going to multiply this by 1 in the form of the square root of 2 over the square root of 2. That will give us the 2 2's that we need to be able to factor out a 2. So 3 times the square root of 2 is our numerator. The square root of 2 times the square root of 2 is just 2. And we're done. We cannot reduce at all. That's just the answer. For number 2, we have the square root of 3 over the square root of 5. We cannot have a square root in our denominator. So we're going to multiply this by the square root of 5 over the square root of 5. It's a form of 1, or it's the number 1 in that form. So in the numerator, we have the square root of 3 times the square root of 5, which is the square root of 3 times 5, or the square root of 15, over the square root of 5 times the square root of 5, which is just 5. Now, the square root of 15 cannot be reduced in any way, and so that is our answer. For number 3, we have the square root of xy over the square root of y. We cannot have that radical in the denominator. We're going to multiply this by 1 in the form of the square root of y over the square root of y. Okay? Now, the square root of xy times the square root of y is the square root of xy squared, right? And the square root of y times the square root of y is just y, but this needs to be simplified. This is a square root with a square in it. That can be factored out. So it ends up being y times the square root of x, because that's left behind, over y. Now, y over y is 1 and can be canceled. So our answer is the square root of x. All right, we've got to simplify and reduce as much as possible till we get to its final form, its smallest form, okay? Okay, let's take a look at the next set of problems. All right, now we can look at number 4. the cubed root of b over the cubed root of a squared b to the third. Now, before we multiply this, we need to simplify, okay? We don't need to multiply and then simplify even further. Let's simplify first and then multiply. This is equal to the cubed root of b over cubed root of b to the cubed is just b times the cubed root of a squared, okay? Don't let them trick you into multiplying first, right? We can simplify first and then multiply. Now we have the cubed root of a squared. We just need one more a to be able to factor out that a, right? To have 3 of them and factor it out. So we're going to multiply by 1 in the form of the cubed root of a over the cubed root of a, okay? In the numerator, we have now the cubed root of ab, right? Of a times b over b, I'll put it here, and then we have times the cubed root of a squared times the cubed root of a. That gives me the cubed root of a to the third power, which is a. There's nothing else that can be reduced or simplified, so that problem is done. For number 5, we have 7 over 3 times the cubed root of 2. We need to get rid of this radical in the denominator. It's not allowed. We have 1 2, but we need 2 more 2's, right? So we're going to multiply by 1 in the form of the cubed root of 4, which is 2 times 2. That's the 2 2's that we need, right? So the cubed root of 4. So that's going to give us in the numerator 7 times the cubed root of 4 over 3 times the cubed root of 2 times the cubed root of 4 is the cubed root of 8, which is 2, right? So we have 7 times the cubed root of 4 over 6. 7 and 6 cannot be reduced, so we are complete. That problem is done. Looking at number 6, we have 5 times the square root of x over 2 times the square root of y. We cannot have this radical in the denominator, so we are going to multiply by 1 in the form of the square root of y over the square root of y, okay? It's going to give me in my numerator 5 times the square root of xy over 2 times the square root of y times the square root of y, which is just y. There's nothing that can be reduced, and so that problem is complete, right? So when we solve these, remember, we cannot have a radical in our denominator. So we need to multiply the fraction by 1 in the form of whatever is going to cancel my denominator, okay? This one was probably, these two here were probably the ones you had to think about the most. In this case, we have a cubed root of a squared. We just needed one more a to be able to have an a to the third power. So that's what we multiplied by, okay? For this one, we had the cubed root of 2. We have 1 2. We needed 2 more 2's to have the 3 2's we need to make it a perfect root. So that's what we multiplied by. All right, and then the rest of it is simply simplifying and reducing where possible. Okay, here we were able to reduce here and have a more simplified answer. That's it for lesson 3. Go ahead and finish the rest of the problems, and I'll meet you back here for lesson 4. Good job. Lesson 4 begins on page 9, and it's completing the square of a quadratic function. Okay, and now it says graphing quadratic functions in vertex form, which is this form. It's not difficult. However, most functions are not in vertex form, but they can be made to be in vertex form by completing the square. Now, we learned completing the square several weeks ago, but this is slightly different because when we're talking about quadratic functions, we have a y equals stuff, right? It's not just the x parts equals 0. So it's a little bit different, but the steps are basically the same. So we're looking at this, y equals x squared minus 6x plus 5, right? We're singling out the x terms, leaving the plus 5 by itself. Now we're still taking this 6, right? Dividing it by 2, we get negative 3. That's what goes in my box, okay? Negative 3 squared is 9. So now inside this parentheses, we've added 9. Now to keep our equation equal, So we're not changing the equation. If we added 9 here, then we need to subtract 9 here. Okay? Then 9 minus 9 is 0. Basically we've added 0 to this equation, and that's what we need to do. So then we know that this is x minus 3, the quantity squared, and then add 5 minus 9 is a negative 4. Now this function, right, this quadratic function is in vertex form, and we can say that the vertex of this function is at positive 3, negative 4. All right, let's take a look at the next example. Y equals 2x squared minus 4x minus 1. Okay, they've separated the x terms, leaving the negative 1 by itself. Then you take, right, then they factored out a 2 because they have a 2 in common. So we can factor out that 2, which leaves x squared minus 2x. Now, we're going to take that 2x, right, and we're going to multiply it by 1/2. And that gives us a 1. 1 is technically a negative 1, right? Squared is equal to 1. So we're going to add a 1 here, but we're subtracting it right there. So keep our equation the same. 1 minus 1 is 0. So basically we've added 0 in the form of 1 minus 1. We know that this now, this part in the parentheses, right, is x minus 1, the quantity squared, and then negative 1 minus 2 is a negative 3. So our vertex for this function is at positive 1, negative 3. Okay? Let's turn the page. At the top of page 10 is the summary of the steps, but there's a couple of special conditions here that we need to go over before we can do some of these problems together, and they only give us 4, so not a lot to practice, but we do know our completing the square. So it says when the quadratic function is a perfect square, such as this, right, x squared minus 2x plus 1, we complete the square, will show this, right? It'll be x minus h, the quantity squared, plus 0, right? The vertex will be at h, comma 0. If you notice a perfect square, simply factor it out without going through the process of completing the square. If you notice it, then you don't have to complete the square. When a quadratic function has a constant but no x term, like this one, y x squared minus 3, then the h value is 0, so it's 0, comma k, right? 0 is here, which is what canceled out the term. So let's look at these examples. Y equals 3x squared minus 5. We don't have an x term. We don't have a linear term. So we know this is going to be 0, comma k. So our vertex is at 0, comma negative 5. All right? Here, this function is a perfect square. It would factor to x plus 3, the quantity squared. So if we wrote that in its standard form, right, we would have y equals x plus 3, the quantity squared, right? That's what it would look like if we factored it. And so it tells us that our parabola has a negative 3 x part of the vertex, right? That's because it made it a positive. We have to switch the sign to get a negative 3, but we don't have a constant over here, so it's going to be at 0. So our vertex is at negative 3, comma 0. All right, let's do these problems together. It's the best way to learn. Okay, Algebra 2, Book 4, Lesson 4, page 10, problem number 1, y equals x squared minus 10x plus 28. Not factorable that I can see. Let's see here. Factors of 28 would be 14 times 2. That's not going to get me here. 4 times 7. No. Okay, so we need to complete our square. Y equals x squared. This is how I like to write it. Minus 10x, and I leave a space, right? Plus 28. You know, the book kind of just put parentheses there. I like to leave the open space. So I have negative 10 times 1/2 is going to give me a negative 5. I need to square that, which is going to give me a 25. So I'm going to add 25 here, but I'm going to subtract 25 there. Okay, 25 minus 25 is 0. I haven't changed the equation at all. So now I can simplify. Y is equal to x minus 5, that's what's in our box, the quantity squared. 28 minus 25 is a plus 3. The instructions here are to change them into vertex form by completing the square. That's what we've done. They want us to graph then problems number 3 and 4. For number 1, I'm also going to list the vertex. So remember, when we list our vertex, okay, it's the opposite of what's in here. So a positive 5, and then just this number. So my vertex for this is at 5, 3. All right. Number 2, y equals 3x squared plus 18x plus 34. So I don't think this is factorable. I'm just going to complete the square. So y is equal to 3x squared plus 18x plus 34. All right. First, I know I can factor something out of here. They definitely have a factor in common, and I'm not talking about the x because that's going to screw it up, but they have a constant in common, right? So y is 3 is what they have in common, right? They both have a 3 in common. So I have x squared plus 6x, right, plus 34. All I've done is factored out a constant from inside here. I probably need one more set of parentheses, technically. Okay. So now I need to complete this square. 6 times 1/2 is 3. 3 squared is 9. So I'm going to add 9, but then I'm going to subtract 9, right? So 0 in the form of 9 minus 9, right? So now I know I can write 3 times x plus 3, the quantity squared. And then what do I have over here? 34 minus 9 is 26, right? Right, is that right? No. Like, wait a minute. That doesn't seem right. Is 25. Okay. That's correct. All right. So, equals. So, where is my vertex here? Well, my vertex is going to be the opposite of here. So, negative 3, comma 25, which is crazy. But there it is. All right. Let's do the next two. So, for number 3, we have y equals x squared minus 2x plus 3. So, this is actually factorable, all right? So we are going to take a look here, although I'm not sure it's going to give us exactly what we need. But let's see here. I don't think it's a perfect square, though. Oh, yeah, it's factorable, but it's not a perfect square. So we are trying to get these, you know, that's in my head that I can factor it, but it's not going to help me with this function. All right, so starting again. Y equals the quantity x squared minus 2x. I'm leaving a space, and then I have this plus 3, right? So negative 2 times 1/2 gives me a negative 1. I'm going to square that, and I get a positive 1. So I'm going to add 1 here, and I'm going to subtract 1 there, right? 0 in the form of 1 minus 1. So now I have y equals the quantity x minus 1 squared, right? That's what's in our box, plus 2. 3 minus 1 is 2. Okay? So now, they want us to graph this one. Don't forget. So where is my vertex here? Where am I starting out? Well, it's the opposite of this. So a positive 1 and a positive 2. This just stays the same. So here's my vertex. Let's just find some, at least one other point that we can graph. Remember, my vertex, my x value of my vertex is a positive 1. That tells me that the axis of symmetry is at that positive 1. So if I go to positive 2 or 0, it should be the same number. So I'm going to put a 0 in. 0 minus 1 is a negative 1. Negative 1 squared is a positive 1. 1 plus 2 is 3, right? So to show you, right, because remember it was the symmetry that we have, I went 1 back from this positive 1 symmetry. So I'm going to go 1 forward to a 2, and it should be exactly the same answer. 2 minus 1 is 1. 1 squared is 1. 1 plus 2 is 3. All right, so we are now ready to graph that. Let me grab some graph paper. Because my graph is positive, right here is a positive 1, right? I know I'm opening upwards. My vertex is at 1, 2. So 1, 2. And then my next set of points is at 0, 3, and 2, 3. Because remember, this is the axis of symmetry right here. So my parabola in general looks like this. Now, it's probably best to have another set of numbers, but it isn't 100% necessary. Okay? Let's take a look at number 4. For number 4, we have y equals x squared plus 6x plus 7. So y equals x squared plus 6x, leave a space, plus 7. 6 times 1/2 equals 3. That's in my box. Squaring it gives me a 9. So plus 9 minus 9. We've added 0 in the form of 9 minus 9. We can now write this as y is equal to the quantity x plus 3, that's what's in my box, squared. 7 minus 9 is minus 2. My vertex is at the opposite of this, so negative 3, comma, negative 2. It still opens up because this is positive. So let's look at some points. Negative 3, okay, is my center, right? That's my axis of symmetry. So I could go to negative 2 or negative 4. I'm going to go to negative 2. Negative 2 plus 3 is a 1. 1 squared is 1. 1 minus 2 is a negative 1. Now, 4 would be the same, right? So if you want to get another point, we could just continue in that same direction and say negative 1. Negative 1 plus 3 is 2. 2 squared is 4. 4 minus 2 is 2. All right, with those points being there, let's get our graph paper again. All right, so we have our vertex at negative 3. 1, 2, 3, negative 2. So right here. And then the extra points that I found were at negative 2, negative 1, which tells me since this is my axis of symmetry, that I have, if I go 1 point to get to the symmetry, I go 1 point past it, and that's the matching point, right? And then I have negative 1, positive 2. If I go towards my symmetry, I went 2 blocks, so I need to go 2 blocks past it, and there's another point, right? That's what it means. We fold it in half, and it would be perfect on both sides. And so there is our parabola for number 4. All right, so make sure you follow the directions. They only wanted you to graph 3 and 4, but we need to make sure we're reading our directions. All right, so that's it for lesson 4. Go ahead and finish the rest of the problems in the lesson. Lesson 5 is the quiz, right? So that'll be handed out in class. If you have any questions, always do not hesitate to contact me. Otherwise, until next time.